Welcome back, everybody. So we are in the last part of Unit 4 here, which is on rational functions and what their graphs look like. So we'll be looking at that, and the key idea is going to be asymptotes. There's really going to be 3 different types of asymptotes that we look for with rational functions. So what we'll note to start is a rational function looks like a ratio of 2 polynomials. So we typically use P and Q, but what we'll note is they are polynomials. So it's going to look like x to the n plus x to the n minus 1, all the way down. So quadratics, cubics, quartics, quintics, linear, constant, all sorts of different functions. So when graphing, we're still going to use kind of all of the sorts of things we would use for any sort of graph. So we're definitely going to use zeros. So values or x-intercepts, values where y is equal to 0. We're definitely going to use y-intercepts. And then we're going to use the asymptotes. So zeros, y-intercepts, asymptotes are kind of the basic feature that we're going to look at. But we're also going to use symmetry. So even and odd symmetry as well. So we'll start by defining kind of these features and then look at how we can graph them. So vertical asymptotes are probably the simplest things to find. This is going to be zeros in the denominator. So if I have x minus 1 over x plus 2, then x equals negative 2 would be my vertical asymptote. And at x equals negative 2, what that's going to look like is the function will approach plus or minus infinity. So it's going to look vertical. So at negative 2, our graph is going to be going extremely upward or extremely downward. Now, horizontal asymptotes are going to have kind of the most analysis required for them. So we'll jump down a little bit to holes here. And so these are going to be factors that cancel in the expression. So these are not vertical asymptotes. So if we had y is equal to x plus 1 over x squared minus 1, we'll factor that as x minus 1 over x plus 1, and those factors will cancel, meaning that there is a hole at x equals negative 1 and a vertical asymptote at x equals 1. So for that graph, you're going to have an asymptote at 1, meaning you're going to have some sort of infinite behavior. But then at negative 1, right, that value is going to be open, whatever that value is approaching. So we'll just put a little open circle to indicate that there's a hole. But let's go ahead and get to horizontal asymptotes. So I'll zoom in a little bit here. So for this, we're going to have to look at the degrees. So note we need to look at the degrees of P and Q. And what we consider for horizontal asymptotes is looking as x goes to plus or minus infinity. So in other words, on our graph, maybe we've got an asymptote somewhere and we've got some sort of infinite behavior. But what we're really going to care about is what is it doing as it goes extremely to the right, so towards positive infinity, or extremely to the left, towards negative infinity. And are there values that we are approaching. Right? So is there some numerical values that we're approaching, or are we just blowing up to infinity as well? So that's going to be kind of our goal to analyze. So when we're looking at the degrees, there are three scenarios. So p of x could be greater than q of x, and note p is the numerator. So that's our top expression, and then q of x is our denominator. So if we look as p of x is greater than q of x, well, if the denominator has a larger degree, is it going to get bigger or is it going to get smaller as we approach infinity if its degree is larger than q? Well, obviously, p of x will dominate the behavior as x goes to positive or negative infinity. Thus, if the numerator is exploding to infinity, q of x is getting big, but it can't keep pace, what we would say then is that the horizontal asymptote does not exist. And what that means is that our graph, so if we've got some vertical asymptote somewhere, let's say, going to positive and negative infinity, it means that our graph is going to be heading upward or downward, right? So our y values are going to be going to infinity, or they're going to be going to negative infinity. So we're going to have a graph where the values at the ends are increasing without bound or decreasing without bound. Oops. And we'll come back to this example in just a moment. So now what if p is less than q? Well, then that means that q of x will dominate the behavior as x goes to positive or negative infinity. Oops. But if q of x is getting much larger, much faster, right, what does that mean that we're approaching? Right, what is our horizontal asymptote going to be approaching, or what is it going to be equal to? Well, let's think of fractions here. So if I had 1 over 2, 1 over 20, 1 over 200, 1 over 2,000, and I continued in this way, what value am I approaching? So take a moment to think about it. Well, we know the number is shrinking, but it's not becoming negative. It's just shrinking. So if I continue to shrink as a positive number or even as a negative number, I'm going to be approaching 0. So our horizontal asymptote is going to be y equals 0. So q of x gobbles up the size of the expression, so it's going to be a gigantic value over underneath a smaller value, and so it's going to be approaching 0. And then finally, if the degree of p is equal to q, then the function will have a horizontal asymptote that looks like y equals a over b, where a and b are the leading coefficients. So in other words, if we have, let me add a new page here. If we have y is equal to 2x squared plus 3x plus 1, and the denominator is 5x squared minus 6x plus 4, then as x goes to infinity, the terms that are smaller in degree become insignificant. And all we care about is this expression, which if we take the ratio, is going to be 2/5. So if I graph this function, no matter what the asymptotes look like, if I look at 2/5 on my y-axis, that's where my function will be above or below as we go towards infinity. And so these are definitely great things to verify on Desmos. So I would play around with some Desmos rational function equations to see what happens with them. What we'll note is from our previous examples, so if I had 2x cubed plus 3x plus 1 over 5x squared minus 6x plus 4, so that first expression up here, but just making the numerator larger degree, then the difference there is that the function is now going to be approaching positive or negative infinity as we go to the right or left. So note, we're looking at the extreme right or the extreme left of our graph. We're not discussing vertical asymptotes. And then if we had 2x squared plus 3x plus 1 over 5x cubed minus 6x plus 4, then that is just going to, like our first example, have a horizontal asymptote, but now it'll be at 0. And again, our graph will be above or below depending on our analysis. So we still need to kind of work out how the graphing analysis is going to look like. But you're really going to have three possible scenarios: approaching a non-zero number, approaching some form of infinity, or approaching 0. So those are the three cases. So now there's one extra possibility, and that is going to come from example number 1. So if we are in the one case, so P is greater than Q, then that means we have some type of slant asymptote. So we'll note this is if the degree of P of x is greater than Q of x. So note the degrees by exactly 1 degree. Then f of x will have a slant asymptote that looks like y equals mx plus b. So we're going to have some line with non-zero slope that our graph is going to be following along. So if we think of those sample graphs I put up a moment ago, so if we've got this sort of infinite behavior as we go to the extreme right or the extreme left, there's going to be some line that those ends will follow. So we'll have vertical asymptotes and slant asymptotes together. So the question is, how do we find these asymptotes if they're slanted? What we're going to need for that is long or synthetic division. So this will be how we find them. So we're going to do some long synthetic division because obviously we're dividing expressions here. So we'll look at the divided expression to figure out our slant asymptote. So for our examples here, so we'll look and notice that we've got 1 degree larger in the numerator than the denominator. So this will have a slant asymptote. So if we want to find just the slant asymptote, we will actually do the long division here. So we've got x squared plus 7x plus 6. So we want to figure out what to multiply x by to get x squared to start, which is just x. So that'll give us x squared minus 3x. Then we'll subtract like we normally do with division. And so 7 minus negative 3 is going to be positive 10. So we'll have 10x plus 6. So then to get 10x from x, we'll have to multiply by 10. So we'll get 10x minus 30. Subtract that, and we'll get 6 minus negative 30 is positive 36. So what we're going to get here, oops, let's use a different color. Is the remainder. So our remainder is 36, and so we'll write that as 36 over x minus 3. So that's going to be our slant asymptote for this equation. The question is, what do I do with that 36 over x minus 3? Because if it looks like y equals mx plus b, that means that my slant asymptote is y is equal to x plus 10. And that's because as x goes to either infinity, extremely to the right or extremely to the left, what happens to 36 over x minus 3? Well, x is going to get really, really large or really, really small. So this is going to shrink to 0. So we can ignore the remainder. And all we need to look at is the linear equation portion of the expression. And obviously, if I'm taking a quadratic divided by a linear, that's going to give me some sort of a linear equation. So y equals x plus 10 would be our slant asymptote. So go ahead and take a moment to do G on your own. So go ahead and pause the video, see what you get. So for this one, I'm going to actually do synthetic division, just as an alternative here. So we'll have 2, x squared's coefficient is 1, x's coefficient is negative 4, and the constant is 3. So note for this, we bring down the first term, and then we multiply, add, multiply, add, multiply, add, until we're done. So we're just going to follow that mama process. So we'll get 2 times 1 is 2. Negative 4 plus 2 is negative 2, and then 2 times negative 2 is negative 4, so we'll get negative 1 when we add. So what that means is that we have x minus 2 minus 1 over x minus 2 is our remainder. So we would get the same thing with our long division, but again, we can ignore the remainder. So our slant asymptote is going to be y equals x minus 2. So if we graph this function, what we're going to do is we're going to sketch where x minus 2 would be roughly located. And then we'll have to sketch our graph from that information. We can see there's a vertical asymptote at 2, which is going to be where the 0 is. So our graph then, if we plot points, we'll have to figure out where this is located. And in the end, what we'll end up with is a graph that follows the slant asymptote to the right and the vertical asymptote to the left for that rightward branch. And then there's going to be a leftward branch that follows that vertical asymptote and then along our slanted asymptote. So note we could get graphs in the future, though, where we're in these two regions. So it's not always going to look the same. So that really kind of covers the basics of what we're going to be doing. Now is going to be actually getting into the graphing. So our guidelines for graphing is going to be kind of as follows. So we want to find zeros, y-intercepts, and factor as much as possible. 2, we'll identify asymptotes. And then 3, we'll graph all of those points and maybe, plot points to verify behavior. And check for symmetry. And note for asymptotes, this is going to be all the asymptotes. So slanted asymptotes or horizontal and vertical, everything together. And holes. Yeah, so holes in our graphs as well. All right, so I'll pause the video here, and then we'll get to actually graphing these examples when we come back. So if you do have questions, shoot me an email, let me know. Otherwise, till I talk to you.